Acha, let's start and quickly recap what we were up to. Acha, you can hear me? Omar, can you hear me? Saim? Alicia, can you hear me?
Yes, sir.
Acha, so we were talking about electrophilic substitution, but we had started talking about electrophilic substitution of 2,4,6 directing groups, which was that what I told you was that you have a like a normal electrophilic substitution where you have an electrophile that's coming in that's attacking the benzene pi electron cloud, where the pi electron cloud is evenly distributed on all the carbon atoms. That was normal electrophilic substitution. And the electrophile could get attracted to any of the p orbital electrons. It could get bond with this one, or it could bond with, because all of them were identical, they almost had the same electron density, so they could bond with any one of them. And in benzene derivative compounds, I told you there are groups that are known as 2,4 directing groups, 2,4,6 directing groups. These groups are alkyl chains or electron donating groups. What happened is that the alkyl chain would push, like if you attach an alkyl chain next to a benzene, the alkyl chain is going to push electrons onto the benzene. So the electron density over here would increase, and all the other electrons in benzene will be repelled by the electrons over here on this side, and they're going to get concentrated on this position number 4. So the electron density is going to be higher at position number 2 and 6, and it will be higher at position number 4 as well. So which is why if you have an electrophile that's coming in, then that electrophile would be a lot more interested in position number 2 or 6 or position number 4. So this is what we discussed. Then we talked about electrophilic substitution of arenes. I told you that if you have a alkyl chain attached to a benzene, the alkyl chain has a very slight electron donating effect, which is why the reaction conditions would almost be the same. It's just going to be very slightly faster. The reason the reactions are going to be faster is that because of the electrons getting pushed or being donated by the group that is attached to it, the electron density on the benzene becomes higher, which is why it's a lot more interested in the NO2 plus 1. So the reaction and the attraction for the electrophile would be slightly stronger. And so we were talking about electrophilic substitution of arenes, and I told you that alkyl chains, they have an electron donating effect, but that's not very high. So the reaction is only going to be very slightly faster, and the electron density would be higher at position number 2, 4, and 6. So the bromine will either be attached at position number 2, or it's going to be attached at position number 4. And nitration would be similar. The NO2 would either be attached at position number 2 or at position number 4. It might get attached to position number 3 as well, but the chances of that happening are going to be lesser. They're going to be lesser. So there's a lower chance of the electrophile getting attached at position numbers 2 and 4. And then in the last class, we started talking about another electron donating group, which is your 2,4,6 directing group. So we talked about another one. And when I say 2,4,6 directing group, I mean an electron donating group. So when it comes to this group, the electron donating effect is really high. And I wrote the word highly activated. That means, and the reason that is high is because oxygen has a bunch of lone pairs. Unlike the carbon chain had nothing to give. It just had a very slight electron donating effect. But an OH group has actual lone pairs, 2 of them, 4 electrons. So there are 1, 2, 3, 4, 5, 6 electrons on the benzene electron cloud. And if you have 4 electrons coming in from the OH, then the electron density would become really, really high. It would almost double. And it would be very high on positions number 2 and 6. And the other electrons would get repelled very strongly, and they would be very high. The electron density would be very high at position number 4 as well. So this is what I wrote, that the lone pair on oxygen, and they're going to ask for the description that the lone pair on oxygen in OH overlaps with benzene's pi electron cloud, which increases its charge density. and also polarizing power. And this time for electrophilic substitution, you don't need a catalyst. So your conditions, they change drastically. The bromine molecule is going to get polarized by the repulsion of the high electron charge density over here. You don't need a catalyst at the other end, which you needed previously. So here's your phenol molecule. It's no catalyst is needed, nothing is needed. So the conditions have changed. Now the thing happens, the reaction happens at room temperature. And not only does one bromine get substituted, it's 3 bromines at all 2, 4, 6 positions that are getting substituted in this particular case. So a bromine gets substituted position numbers 2, 4, and 6, all of them. So you get a lot of electrophilic substitution, and you get 2,4,6 tribromophenol. I told you that this bromination reaction was also a test for identifying phenols, that you get a white precipitate, and the red-brown bromine gets decolorized. But along with that, you get a white precipitate of 2,4,6 tribromophenol. This is phenol, okay? You clear? Is this clear?
Yes, sir.
So now let's talk about nitration now. And I'm going to talk about nitration because remember, there were 2 electrophilic substitution reactions. There was bromination, and then there was nitration. So I'll just copy the same and use that for nitration. So the first one is for nitration. That's also easy. So let me erase this, all of this. So now this one. Again, no catalyst is needed for nitration. You just need concentrated. Nitric acid. That's it. No catalyst is required. Previously, you needed concentrated sulfuric acid as well. This time, it's not needed. You don't need to create the NO2 plus 1 electrophile now, because the polarizing power would be so high that the NO2 plus 1 will, the nitric acid molecule is going to be polarized on its own. And the same thing happens. You'll have, instead of 3 bromines, this time you'll have 3 NO2 groups that are going to get attached to it. And there's going to be an NO2 group that's going to be attached over here as well. And you can leave that. And this is going to be called 2,4,6 nitrophenol. So let me change this. So everything kind of remains the same. Again, no catalyst is needed. This would be called tri-nitro and phenol. This one is not a white precipitate, so we can leave that. So that's trinitrophenol. So remember, reactions are a lot faster, a lot rigorous, and so that's the difference when you have phenols. And for nitration, there's another one, and that one is that the reaction will also happen with dilute nitric acid. It's also going to happen with dilute nitric acid. Again, no catalyst is needed. So there are 2 nitration reactions. One is with dilute. The other one is, the only difference between the 2 is that in dilute, you don't get so many NO2 groups. Again, you don't need any catalyst. But this time what will happen is you'll get 2 products. One of them would be either the NO2 gets attached at position number 2. That's 1. So you just call it, you're going to call it just 2-nitrophenol. That's it. So that's going to be the name of the molecule. And the other one is that it's going to get attached to position number 4 as well. So that would be, let's change this one. So the NO2 will not be here, and instead it's going to be here. And this would be called your 4-nitrophenol. So nitration, there would be two reactions. One would be with dilute nitric acid, and the other one would be with concentrated nitric acid. That's the only difference between the two. With concentrated, you're going to get 3 NO2s. With dilute, you're going to get just 1 NO2, either at 2 or at 4. So ये सारा is this clear? Phenols, right? Is this clear?
Yes. Sir, why does water make a difference?
Dilute and concentrated.
Yeah, why are these two different?
I mean, if it's
What does
simple, I mean, it's simple that if you have concentrated, so there would be a lot of NO2 groups around it. So there's going to be more nitration that's going to happen.
Oh, okay.
A dilute may there would be lesser nitric acid molecules. So obviously the chances of the reaction happening would be lesser as well. So you might at best get 1 NO2. That's about it. Okay. And for the same, remember electrophilic substitution of phenylamines is going to be exactly the same. So this is for phenols. This entire thing that we did, that's for phenols. For phenylamine, it's exactly the same. So I'm not going to repeat everything. It's just that so I'll just do electrophilic substitution and I'll just write so electrophilic substitution or E.S. Let me write the whole thing. So electrophilic substitution of phenols, no, of phenylamine. So just remember all the reasons, everything is the same as, it's going to be exactly the same as phenols. So it's going to be exactly the same as phenols. The whole concept of the benzene becoming increasing its charge density would be exactly the same, except you won't have an OH group. Instead, you'll have an NH2 group. So if I just repeat this thing, instead over here, the bromine molecule is going to get polarized, but the charge density over here is increasing because there is an NH2 group. And the NH2 has lone pairs, and those lone pairs also overlap with benzene electron cloud. So pretty much everything else kind of follows and it's exactly the same. The same as above, and we can sort of copy these quickly. And all we have to do is we just have to change. It's not going to be a test. The only thing we have to do now is we just have to change the OH with, or replace the OH with NH2. So we can, let me just quickly do that. So instead of OH, there's NH2 here as well. This one is not a test for phenylamine, so we'll, and this thing is going to be tribromophenylamine. That would be the name of the molecule. The bottom one, I'm going to just change the OH and replace it with NH2. And this one with NH2. And the name of the molecule would be trinitro, but it's going to be not phenol, but phenylamine. So we've changed that, and this one as well. So everything is exactly identical. So NH2. So you're going to get two types of compounds. One of them would be 2-nitrophenylamine. And the other one would also be 4-nitrophenylamine. Okay, so just remember that electrophilic substitution is going to be identical. So it's going to be exactly the same. Is this clear? So we did electrophilic substitution of 3, 4, 2, 4, 6 directing groups. We did it for, we did electrophilic substitution of phenols. Where did we start? Just a second. This one, we did electrophilic substitution of arenes, the one with alkyl chains, and I told you the conditions remain the same except that it's got a 2,4,6 directing effect. And with NH2NOH, you had a much higher electron donating effect, which is why the reactions were a lot faster, and you didn't need catalysts for that. Okay, so that is the only difference. Is this clear?
Yes, sir.
And then you have the opposite. Now the opposite is 3,5 directing groups. Okay, what happens in the opposite scenario is that in that case there's a 3,5 directing effect that is happening. So this is exactly the opposite of what we studied. And in this case, the reactions are going to be actually either they're not going to happen or they're very difficult to happen. So 3,5 directing groups. Now 3,5 directing groups are electron withdrawing groups. So these are your electron withdrawing groups, and in this case, if I have a 3,5 electron withdrawing group, what are your electron withdrawing groups? It's like an aldehyde is an electron withdrawing group. Like if you attach it to something or anything, the overall effect would be that the oxygen will be pulling electrons away from whatever it's attached to. Carboxylic acids have an electron withdrawing effect. So they also have an electron withdrawing effect. Your data booklet actually used to contain all these groups for reference. So we can have a look at the data booklet and copy the complete table from that. So this one. So this is written. This is 3 position. This is the 2,4 position. So we can copy this table and just put it over here. Now the data booklet won't be there, so it's better to actually remember this. So this one, this was the one that we earlier studied, that NH2OH. And you had the alkyl chains. These were the common ones. We'll study Cl later on as well, but at the moment we don't have to discuss electrophilic substitution. So we just discussed previously, we discussed electrophilic substitution involving, and we were specifically discussing electrophilic substitution involving NH2OH and alkyl chains. For amines, we don't have to discuss. And these are your electron withdrawing groups, like an aldehyde or a ketone or carboxylic acid. NO2 has an electron withdrawing effect as well. So these are some of the groups that are, so we are studying these ones, the ones that have electron withdrawing effect. And what they will do is they'll decrease electron density on the benzene ring. So if I have a benzene ring, they'll pull electron density away from it. So let's say here's my benzene, and I've got an electron withdrawing group attached to it. So there is C double bond O and H. So the electrons are being pulled away. So they are getting pulled away. So now for the same reason, previously the electron density was higher at position number 2 and 4 and 6. Now for the same reason, the electrons are moving in the other direction, in the opposite direction. So the electron density is actually lesser at position numbers 2 and 6, and all the other electrons from the other side would also get pulled because there's a net effect that this oxygen is pulling all the electrons to the right. So the electron density would also be lesser at position number 2, 4, and 6. So previously the electron density was actually higher at position number 2, 4, 6. Now because of the reverse effect, the electron density is actually lesser, and it's overall lesser because overall the electron density on benzene decreases because it's being pulled by the atom on the right side. So electron density on benzene by electron cloud it decreases. And if it decreases, there's going to be lesser attraction for electrophiles. So there's lesser attraction for electrophiles. So electrophiles won't be interested in a molecule that is, so this is called a deactivated benzene. TK, is this clear?
Yes, sir.
This one is known as a deactivated benzene. So it's probably not going to have electrophilic substitution reactions, or electrophilic substitution reactions in this case would be kind of next to very difficult. But they might give you a question. So if an electrophile is interested, then the electrophile would be a lot more interested at position numbers 3 and position numbers 5, because that's where the electron density is still significantly stronger. So it's significantly stronger compared to the other parts, because on positions number 2 and 6, the electron density got pulled away. So the electron density is really low at this position, and all the other electrons from the other side, opposite side, they also have a slide. They got pulled towards the right. So electron density is also lesser at position number 4. So which is why you will have slightly more electron density at positions number 3 and 5. So that's where your electrophiles would probably end up. So the conditions, you don't have to remember the conditions. You don't have to remember any details about any of this, but they might give you a question and they might ask you to write or predict what the product is going to be.
So why is this a deactivated benzene?
क्योंकि वो electrons जो है वो किसके पास चले गए? इसके पास, right?
किसके पास?
मतलब इसके पास.
अच्छा, OH के पास, ठीक है.
तो अब वो जो इशू ये कि वो जो electrophile था, where was the electrophile? Okay, 1 second. अच्छा नहीं, वो मैं कह रहा था कि you had where's the electrophile? This NO2 plus 1, right? This NO2 plus 1 will not be interested in the electron cloud because these electrons got pulled. They'll be pulled away. So the benzene electron cloud would not be that attractive for this positive charge or positively charged electrophile. So which is why the reactions are not going to happen, or they're going to happen with a lot of difficulty. So it's known as a deactivating group. But anyways, they might ask you still to predict what the products are going to be. So maybe there's a reaction. You don't have to go into a lot of details. The only thing you have to know is that if there is still a reaction that's happening, whatever the conditions, like somebody added bromine and FeBr3, maybe they gave it in the question. I mean, you would definitely need a catalyst, because without the catalyst, the reaction will not happen in this case. The only thing you should be able to predict is where would the bromines get attached to. The bromines will get attached to positions number 3 or 5. So it's going to get attached to either position number 3 or 5. So that's where bromine will get attached to. So that's about it. So this is pretty much all electrophilic substitution. There's 2 more reactions, but for that you don't need to know the mechanism. So we can quickly summarize this in a chart. Okay, let me just post one chart so that we have an overview as well. One second. This one. Just a second. It's with this one. I'll just take. I mean, I'll probably send this over. This is just a summary of what's going on, but you have to remember the details as well. So we started at this point, like benzene. We haven't done these bromination. Benzene requires catalyst. Chlorination requires catalyst. You get a bromine or chlorine attached to it. You need concentrate sulfuric acid or concentrate nitric acid. The Na2 gets substituted. But if you have an arene, like if there's an arene anywhere, like if you have an arene, the reactions for arenes are going to be a lot faster. Maybe that's I mean, for OH and NH2, the reactions are a lot faster. But forget this, I'll make a simpler one. This one has all the reactions, so this will kind of confuse you at the moment. We'll probably refer to that once we have done more reactions. So just remember electrophilic substitution, normal benzene, arenes have similar reactions, but phenols and phenylamines, they have a lot faster reaction, and that's pretty much it. You have 2,4,6 directing groups and you've got 3,5 directing groups. Now the next one is known as alkylation and acylation. So it's a simple reaction and it's an electrophilic substitution reaction as well.
So bromine will attach to, I mean, carbon number 3 or 5, right?
Is case when if you have a 3,5 directing group, right? So for a 3,5 directing group, just remember that it has electron withdrawing effect. That's about it. And the electron density becomes lesser. So they might ask you, okay, why is the reaction slow? It's slow because the electron density gets pulled or withdrawn by the group that's attached to it, whatever that group is. And these are the groups. You could have any of these groups. And the other thing is, the electron density would be a lot lower at positions number 2 and 6, and also at position number 4. So if there is an electrophilic substitution, like with bromine or with NO2, then it would most likely end up at positions number 3 or at position number 5, which is kind of the same position. TK, is that clear?
Jason.
So the other ones, you've got alkylation. Alkylation is, I mean, it is an electrophilic substitution reaction, but you don't have to sort of link it up with that. In alkylation, what happens is you attach, alkyl chain gets attached to it, to benzene. So it gets attached to benzene. The mechanism and everything else is kind of similar. Just one second. anyways, it gets attached to benzene. So I'll quickly draw a benzene. What will happen in this case is that that if you have a benzene,
Then, sir, how does it differ from an arene?
because my alkylation,
Yes.
alkylation produces an arene.
Oh, okay.
Okay, but you start off with a benzene and then it eventually produces an arene. So anyway, so you have a benzene and you have to attach an alkyl chain next to it. So what you'll do is you'll bring in a halogenoalkane. There's going to be a halogenoalkane like let's say there's a carbon chain, CH2, CH3, and there is a Cl. And this one has two hydrogens. Okay, so I'm drawing it in a way so that I can attach the molecule. Now, what will happen is that the carbon and Cl bond is polar. So carbon has a slight, it's got a slight positive charge, and the Cl has a slight negative charge. So there's a halogenoalkane that's coming in. The halogenoalkane is going to act as an electrophile. Why it's going to act as an electrophile is because carbon has a positive charge. So you don't need to, no need for the mechanism. TK mechanism, just ignore the mechanism. So mechanism in this case is not, it's not required. But I'll just explain this very quickly. The electron cloud and benzene are going to get attracted to the positive carbon atom. And the Cl electrons are going to get repelled. So what the benzene would do is that it's going to repel the electrons in the carbon Cl bond, and it will attract the positive carbon atom. So that's about it. And in this case as well, because it's a benzene, you would need a catalyst. So the reaction does include a catalyst. The product would be that the Cl would eventually break off. So if I draw this again, the Cl is going to leave. And what you'll eventually have is the Cl is going to leave. It's going to get repelled by the benzene, and the carbon chain will get closer and closer to benzene, and eventually it's going to bond with it in exactly the same way. It's going to be another electrophilic substitution reaction, the way it happened previously as well. And the carbon is going to bond with one of the it's going to substitute one of the hydrogen atoms, and that hydrogen atom would eventually go, and the Cl that is broken off would eventually, the two would form HCl. So this is what's happening. Now, all you have to remember is the mechanism is not important. Why this reaction is happening, that's not important. What is important is you should know that if there's a halogenoalkane, which one of the carbon atoms is going to go and attach itself to the benzene. These carbon atoms are non-polar. It's only this carbon atom that has a slight positive charge, and it's this one that would eventually go and get attracted to the benzene electron cloud, and it's going to bond with it. And you got an arene now. You've got a carbon chain that's attached to benzene. So this is a propyl chain or branch which is attached to benzene. So it's propyl benzene. Is this clear?
Yes, sir.
ठीक है, Alicia, is this clear? Bakiyon clear? Umar, Saim, is this clear?
Yes, sir.
And you would also need an AlCl3 catalyst for this because it's obviously it's similar to the electrophilic substitution that you did earlier. There's going to be a catalyst on the other side that would be pulling or attracting the Cl, but you don't need to know the mechanism. You just need to know which carbon would get attached to it. So if I do the reaction again, we're going to try and predict what type of arene would be formed. So for example, if I have let's say I have a tertiary halogenoalkane, and the tertiary halogenoalkane kind of looks like this. It's got So it's got this carbon chain, and there's a Cl attached over here. This would have 3 hydrogens, this would have 3 hydrogens, and you'll have, this one will have 2 hydrogens, and this one will have 3 hydrogens. And if I do a reaction, and there's an AlCl3 catalyst involved as well. So in this case, you have to predict what the product is going to be. The product is going to be that it's going to be this carbon atom that is over here, which has a positive charge. The Cl will break off the benzene, any of the electrons, any of the carbon atoms, because this is there's going to be an equal probability of this carbon atom getting attached to any one of them. If it had been a phenol, or if it had been something else, then the probability at positions 2, 4, 6 or positions 3, 5 would increase. But over here, it's an equal probability. So I'm going to take this, I'm going to attach the carbon chain. And what people, mostly the mistake that is made is that they attach the wrong carbon atom. So I'm just going to highlight that carbon atom, the one that we are trying to attach. It's this one. The arrangement around that should remain exactly the same. So think of it as this carbon atom that I've circled. This carbon atom, the Cl has left. This carbon atom has gone and bonded with it. It's got 2 CH3s and 2 CH2CH3 around it. So it's got 2 CH3s. And it's got a CH2 and another CH3 around it. Okay, so that's alkylation. Is this clear?
Yes.
Yes.
Okay. So just remember which specific, because the carbon chain will have a lot of carbons, you have to remember where exactly is the benzene getting attached to. It's not going to attach to any of the other carbon atoms because they're non-polar. It's going to get attached to the carbon that's polar. And so that's how you attach a carbon chain to benzene. Then there's another reaction, and that's known as acylation, which is kind of similar, but it involves an acyl chloride. So acylation is...
Sir, and I mean the carbon that is being attached to the benzene, I mean it can get attached to any of the numbered benzene. मतलब उसमें तो फिर ये नहीं है ना कि carbon number 3, 4.
देखो इस केस में तो they're all equal, right? The electron density is exactly the same, right? हाँ, लेकिन if it had,
if it was वो दूसरा वाला,
हाँ, so if it had been, so you have to remember that, because remember I called this is electrophilic substitution. So if there was an OH group attached or an alkyl group that's already attached to it, or an NH2 group attached, then that carbon will find positions 2 or 4. Or if it had been an electron withdrawing group, then it will attach to position number 3. But otherwise, if it's a normal benzene, it's going to get attached anywhere, okay? Or any of the carbon atoms. Actually, next one is acylation. So let's finish that one as well. So you have acylation. Now, acylation is exactly the same as before, the one that we just did, except for one difference that it involves an acyl chloride, which is like let me just copy one of the benzenes. So if I take a benzene and I put it here, now this is what an acyl chloride is. An acyl chloride is that it has a carbon chain. So let's say you have CH3, you've got CH2, you've got another CH2, and there's a C double bond O and Cl. So just like a carboxylic acid, this is your acyl functional group. So an acyl chloride is going to be RC, there's going to be a double bond O, and there's going to be a Cl. Okay, that's what your acyl chloride is. Now, which of the carbon atoms is polar? It's this one. This is the carbon atom that's highly polar. So again, the mechanism is not important. So this carbon is the one that's going to be interested in the electron cloud of benzene, and the Cl would get knocked out. So something very similar happens, and you get the same thing. It's the Cl gets knocked out because the Cl is already negatively charged. So I'm just going to attach the two now. And even in this case, you would need a catalyst. So this one, the Cl gets knocked out. It ends up forming HCl. This carbon is the one that's got a positive charge. So we can kind of rotate this and or maybe put this straight and get the benzene to the other side. So this thing. And what will happen is that this carbon will get attached to one of the benzene atoms, benzene carbon atoms. And again, HCl is going to be produced because the H is going to get substituted onto the on the benzene, and the Cl has already left. So they're going to end up forming HCl, and again, you would need a catalyst in the form of AlCl Cl3. That catalyst would be needed. So that is acylation. So the only difference between the two are very similar, alkylation and acylation. Over there, you have a halogenoalkane. So you just have a carbon chain that's getting attached to it. Over here, you have a carbon chain with a C bond O and Cl. So the carbon is positive. So that carbon atom, there's a C bond O that's coming in as well. So this is like a ketone with one side having a benzene and the other side having an alkyl chain. So this is acylation of benzene, that an acyl chloride gets attached to benzene. And that's about it. So these are two reactions, and that pretty much sums up electrophilic substitution. So remember, two mechanisms, nitration and bromination. Benzenes, you have to remember the mechanism. You have to remember the 2,4,6 directing effect. You have to remember that arenes and benzene almost have similar reactions, except for the directing effect. And phenols and phenylamines have a lot faster reaction. And at the end of the day, there are two more electrophilic substitution reactions which include alkylation and acylation. Is that clear?
Yes, sir.
Okay, so this is all electrophilic substitution. The next thing that we're going to talk about is hydrolysis. We're going to talk about, so remember, what we're going to do is, most questions about electrophilic substitution would be a comparison of different things, different benzene-related compounds. They might be talking about alkylation, they might be talking about electrophilic substitution phenols, they might be comparing it with benzene, etc. So electrophilic substitution, we're done with all types of electrophilic substitution that is related to benzene and any of its derivative compounds. So next class, we'll study hydrolysis, and we'll compare all types of compounds who are going to get hydrolyzed. Okay. So this is one part. We're done with one part, and we're done with benzene mostly. Okay. The hydrolysis and the other parts will not involve that much benzene. This is the one that has more benzene in it. Okay. Let's continue tomorrow then. Okay. Okay, everyone. Allah Hafiz.
Thank you, sir. Allah Hafiz.